I think this is basically where we stopped here. Actually, this is an exercise we all know how to do. In this case, this is done optimally, right? But I wanted to show you this so that you also realize that in practice, we really need eventually the computer to solve this sophisticated task of training, of optimizing the parameters on a large language model, for instance, to solve the supervised learning problem. If we will do it ourselves, we will never find the optimal solution. The same way as if we park ourselves, probably we will not do it as well as this computer driver is doing, right? In this case, the control has been computed so to minimize the length of the curve that we draw when parking, right? So probably most of us, when trying to park the car in this way, we will need maybe another iteration, another move forward and backward in order to succeed. And so this is the first thing. So in control theory, you will typically find theorems that say there exists a control. The control can be characterized as the so-called optimality principle or Pontryagin principle. It's just the classical equations of Euler-Lagrange for the minimizer. You can characterize the optimal control, but finding the optimal control is something that normally you cannot do, except very few, very simple examples where you can do it analytically. Most often, the optimal control will be, led to the computer, okay? And this happens in these very simple examples. You can imagine when you are dealing with, these big problems of machine learning, where you have to train models in which you have billions of parameters to be optimized. That's simply impossible for humans, right? And this is very much consistent also with this bitter lesson of Shatton, right? So we can, as humans, build the models, but the computer has to do the work. Another aspect that you see in this video is that this idea of switching, right? So what are we doing? You see, we move forward and then stop. So it's 1, 0. And then it's 1 again. But once you are there, we rotate. So it means that there are actually two controls. There is a control U and there is a control V. The control U is acceleration, and the control V is rotation, right? So if we think that U is just forward or backward acceleration, and V is rotation, either left or right, so what are we doing here? What are we doing? So we do first 1 for U, then 0. Then 1 for U again. Then 0, stop. Then we rotate with V. 1 for V, stop, 0. Then we rotate V in the opposite direction, -1 for V. Right. And then, right. And actually, if you look closer, you see that it's even a bit more complicated than I said, because now we do U equal 1, now 0, both of them 0. Now we do again U equal to 1, now 0. Now we rotate with V, we do -1, but also U is -1 because the car is going backwards, and then 0, 0 again. and then we rotate V in the other direction, we do 1, but the car is going back, so it's -1. And then we move forward. So you see, the control will be something like 1, 0, then 0, 0, and then 1, 0, and then 0, 0, and then is something like -1, -1, and then is what, 0, 0, and then is, I think is -1, +1. Okay, you see? We could complete. Let's check. So the control is 1, 0, now 0, 0. Then is 1, 0 again, then is 0, 0. Then is -1, -1, backwards, rotating to the left. Then stop, 0, 0. Then we go backwards, -1, but we rotate to the right. And then we stop for a while. And then finally we do 1, 0. This is what, and if you draw on the time direction, right? So if you will draw, right? You will see that the lags in which the controls are 0 are not always the same. Right? It depends also how many measurements you have to take. Depending on the complexity of the measurements you have to take, you might need more time in pause, okay? So you see the strategy is a switching strategy in some sense, right? So it's piecewise constant. And it's switching. But this is very much what we did in our simulation of how data are classified by the neural differential equation, by cutting with different hyperplanes and moving in different directions. So we do it in an iterative manner, but and the motions are piecewise constant. I can choose just a hyperplane and then the motion, constant motion vertically or horizontally, right? So the controls are piecewise constant, but we are switching. We move from one to the next, okay? Very good. And this is what actually is represented in the rank condition of Kalman. So what the rank condition of Kalman says is, well, you see, in principle, you have only as many controls as the matrix B has columns. For instance, I was discussing yesterday the very extreme case where even if the dimension of the system is D, right? So D is the dimension, for instance, of our WeChat network, right? But there is only one influencer, M equal 1. So only the professor is sending news, right? The professor is saying, so do this, read this, solve this exercise, write this MATLAB program, write this Python program, please send back the output of the numerical simulation you perform, and so on. So there is only one control, for instance. Then now, in this rank, what do you see? If there is only one control, B is just a column vector. Now you multiply A with B and you get another column vector. And so on. So every time you add here one term, you are adding one column vector. So eventually, you have here a D by D matrix. Okay? And we are asking the matrix to be of rank D. It means all these vectors are linearly independent. Okay? So what means is that eventually, by combining the action of the control, as here, active or inactive, and the motion of the system, then, right, then you can achieve the same impact as if you had are all those many controls. So for instance, what is the reason for doing, control and then 0, 0? Think here, right? You say, oh, I was controlling u equal 1, and then I stop controlling. The fact that you stop controlling, you do first 1 and then 0. The 0 has an impact on the system. Why? Because while the control is 0, the dynamics continues evolving. So the next time you act with the control, you are achieving something different because you are on a different configuration. So, and all these possible tricks, all you can achieve by combining the controls and also the fact that the controls are off and you are just enjoying of the free dynamics of the system, all these possibilities are encoded in this rank condition. Okay? If the rank is full, the system is controllable. If not, it's not, right? So you see that even very small dimensional control systems can be quite complex. This explains the complexity of the training process of large, high-dimensional neural networks, because we are dealing with, as we have explained, essentially control problems. Okay? And this is what we have seen in our, in our previous slides, where we have indicated the clear link between control and machine learning. Okay, so yesterday we explained all this. So as I said, all this is very much related to the theory of nonlinear approximation that started with the pioneering paper by Wiener. And then you can find, several articles and books written on this. So for instance, there is this well-known survey article by Ron DeVore on neural network approximation. There are also, of course, some people ask me about references. There are so many references in this field. It's very hard to say one reference. There is, for instance, this paper by Jan LeCun, which is a draft. It's unfinished, right? So actually, he explains in the introduction of this paper that this is kind of some unfinished notes that he, make them evolve. I think they are posted in archive. Well, it's very good to see also not only, the description of the science that has been done in this field, but also the people, how, the leaders in this field think on what the future of the field should be, what the priorities should be for future investigation. And I think for young people, it's always good to have in mind how they view the field. Of course, this is a field where there is lots to be done, right? In particular, because there are many different architectures of neural networks that have been considered adapted to different tasks, right? Nowadays, people are very much using large language models, right? There are many different types of architectures, and you could, of course, consider all the questions I have tackled here for each of these architectures, and each of them will be a very interesting mathematical exercise, out of which you will certainly learn a lot and probably also provide very interesting explanations of why, each architecture is better adapted to the problem under consideration. But let me move to the next topic. So that was actually the title of the lectures was PDEs meet machine learning. So now, until now, I was mainly discussing the problems of machine learning, like supervised learning, explaining how this is tackled, and trying to explain you also why all this works very well, inspired in particular in two foundational types of results. One, functional analysis, the principle of universal approximation, and the other one, control theory, okay? But as I said in the introduction the first day, as for us as applied mathematicians, it's very natural also to think, oh, you know, I'm not satisfied by just understanding and explaining why this works. This was interesting, but I would like also to use it, right? And then the question is, how can I use, or can I use at all, these kind of ideas, for instance, for solving partial differential equations? Now, solving partial differential equations is the central topic in, you know, contemporary applied mathematics. And there is, of course, much more. There is modeling, there is solving the PDE, there is numerically computing the solution of the PDE. There are many different considerations about optimization, control, inverse problems, you know, asymptotic dynamics, singularity formation. There are many, many different questions you can look at. But to begin with, you know, solving the PDE is probably the most central question, the first question. So do I have a good understanding of the existence and uniqueness of the solutions? So now, how is this done in the modern PDE theory? How is this done in modern PDE theory? Well, if you look to the classical books, you know, how, for instance, the Laplace equation was solved on a given bounded domain for the Dirichlet problem, you will see, you know, the classical books. You find this theory also in the book by Evans, for instance, the classical PDE theory. They were using the green function, right? So if you recall, so the green function was a function gxc, right? So that whenever you write ux equal to the integral over omega of gx c dxc, sorry, fc dxc, you get the solution of this problem. Right? So this was the classical idea in 20th, you know, in the 19th century, how to solve this and many other partial differential equations. The idea was to adopt this kind of operator representation ansatz and try to build the function g. But the question was, you know, how do I build the function g, the green function g? That's not an easy one, right? So, and then, for instance, given a domain omega, the g turns out to be the solution of the same PDE that has a, you know, source located at each point xi. So, in some sense, it was a very nice analytical theory, but it was not very easy to manipulate, to use. Why? Because, you know, I just wanted to solve this problem for a given f of x. And now when I open the book says, oh, to solve this, I have to compute g. And to compute g, I have to solve the same equation, but now where f is any Dirac delta located in all possible points. So, well, you know, I have one PDE problem, and now I have a continuum of PDE problems because I have a different PDE problem for every location of the Dirac delta. That was, I mean, very beautiful. And there were, you know, like theorems showing the existence and the uniqueness of the green function, the regularity of the green function, and making, you know, all this theory coherent, but it was too complicated. So it was David Hilbert who had the idea of, you know, making this problem to be much easier to handle, right? He has the vision, you see, this has to have a solution very much like in linear algebra, right? So what can we do in linear algebra? Assume I have to solve this system. So A now is a matrix, D times D. A is symmetric, and A is definite positive. So given B in RD, the question is, how do I compute the solution X in RD? Well, of course, you can always say, well, X is well defined, and X is A minus 1 times B. You can always say, well, you invert the matrix A and multiply B by the inverse of A, you will get the solution X. Yes, this is the theoretical answer. But this is very much the same as saying, for solving the Laplace equation with a given f, you have to compute the green function, right? Because actually computing the green function is more complex than solving the PDE for the given f. So the same here. Computing the inverse of A is more complicated than simply computing the solution X. And this is something that was observed, for instance, by Gauss, right? So Gauss elimination, we all know, is very easy to implement. It can take time if the system is of a big size, but it's very elementary. We bring any linear system into a triangular form so that in cascade, right, you can explicitly compute one and then the other and then the other and then the other solution, components of the solution explicitly, right? So this certainly can be done either by inverting the matrix A or by applying Gauss elimination. But in fact, there is even a very interesting way of doing this is by the calculus of variations, right? Right? So if we minimize the functional half AXX minus BX, right? When we minimize this functional, then it's an easy exercise. You can check yourself. The minimum of this functional exists, and the minimum of this functional is the unique solution of the equation AX equal B. Of course, for this to be done, right, you need the matrix A to be symmetric. You can also check yourself that if you take A non-symmetric and you minimize this functional, even if A is coercive, then the functional will be coercive and the maximum will exist, but then you will not solve the problem with the original A, but you will only solve the problem out of A with the symmetric part of A plus A transpose divided by 2. Okay? So Hilbert knew all this, and he said, well, we should be able to, this was like in 1900, right? So 125 years ago. He said, we should be able to solve elliptic equations very much like in linear algebra by a minimization principle. As I said, so here the goal is, you minimize this in RD. You minimize this in RD. and you get X, which is precisely the solution you were looking for. And minimizing this function is convex, is continuous, is coercive. Minimizing this function is very easy. You can apply, gradient descent, right? And, as explained yesterday by Professor Zhao, if you are in very high dimension, maybe you might want even to apply some kind of, random batch or some stochastic version of this descent algorithm to make, the computation faster, okay? So Hilbert knew all this. And he had the vision, we should try to adapt this methodology for solving elliptic equations, right? But at that time, he knew how to do this formal computation, is by now the classical variational, right, formulation of the PDE. He knew how to do integration by parts. This is why we call it the green, the green formula, right? The green formula of integration by parts. So he knew how to multiply the equation by a test function and integrate by parts to get this variational formulation. He also knew that, this variational formulation was the first derivative, now we call it Gateau derivative, the directional derivative of this functional here. But at that time, there were not Sobolev spaces. Sobolev came much later, right? So when were Sobolev spaces introduced? Maybe does anyone have DeepSeek here? Can you check when Sobolev spaces were introduced? Maybe this was done in the 30s or so. So when were Sobolev spaces introduced? 35? Yeah, but you see, Hilbert was doing this in 1900, 35 years before. So he had the idea of doing this 35 years before we knew well what are Sobolev spaces. Now we know. Now we know that if you want to solve the Laplace equation properly, you have to do it in the Sobolev space H10. I will not enter into the details. Either you know it and then you don't need it, or if you don't know it, then you will need certainly more time to learn about this. But nowadays, we know what the proper Hilbert space is. It's the space of functions in L2, whose first distributional derivative is in L2, whose values or traces on the boundary vanish, so that, they are adapted to the Dirichlet problem. And this is a Hilbert space in which you can guarantee that this functional, which is quadratic, convex, continuous, and coercive, has a unique minimizer. And this unique minimizer is the weak solution, the unique solution in this weak form of the partial differential equation. That was an extremely important breakthrough in analysis of partial differential equation that came soon after Hilbert had this proposal, and this led to a very substantial development of functional analysis, right? So to get introduced to, to this topic, you can have a look to the book of Bresis, for instance, or the book of Evans. Yesterday I mentioned the book by Ciarlet on functional analysis for PDEs. So there are several very nice books that will introduce you to the basics of this very fertile topic, right? So, but of course, if if this is the point of view we adopt, this is still far from practice. Because, yes, we can claim that due to the direct method of the calculus of variation, this functional being continuous, convex, and coercive has a unique minimizer. But this doesn't tell us how I'm going to achieve this minimizer. Actually, these Sobolev spaces are infinite dimensional spaces. So these are very nice abstract concepts. But being infinite dimensional spaces, we don't know how to operate on them. So it took some time until the finite element method was introduced. Can you please ask to DeepSeek when the finite element method was introduced? Maybe the origins are not 100% clear because this was done in part by engineers, in part by mathematicians. Right, in the 40s. So it took just a little time, was during Second World War, more or less, that people realized, if, once we have understood Hilbert, we understood what Hilbert had in mind. Took us, 35 years to build these Sobolev spaces, but now we know. Once we know this, we can easily build finite element methods. The idea was extremely simple, but also very, very useful and impactful. And this is probably one of the great breakthroughs in applied math. So people said, typically functions in H10 can be, more or less regular. It can be, for instance, in H10, you can have also functions with peaks, right? Functions can be smooth. This is, as I said, an infinite dimensional dynamical system, but it's very easy to approximate these functions by functions that are just P1 finite element functions, right? So how do we do it? We take the interval and we split it, right, into, n nodes. We fix the grid. In finite element method, we fix the grid, right? It can be uniform or non-uniform. You fix the grid. And then you say, within this grid, I let myself consider, any function that is piecewise linear and continuous. So the finite element theory guarantees is that when n goes to infinity, right? When n goes to infinity, these functions end up approximating every general continuous function. Actually, if you will plot it in the computer, right? You will take, in your computer, you will plot the smooth function you are trying to approximate. Of course, when you take a very coarse grid, if you take a very coarse grid, the approximation will be very, very rough. The approximation will be something like this. You say, the approximation is very far. But as soon as you take the grid wide enough and you plot the finite element solution in the computer, you will hardly see the difference. So this approximation is really very efficient. As soon as you start increasing, the number of nodes, the level of approximation of piecewise linear function is very, very accurate, right? And this is what led to, the modern theory of finite element method. People said, well, then maybe following the idea of Hilbert, what we should do is, instead of minimizing this quadratic convex function in an infinite dimensional space that we don't really know how to do, let us write, the same problem, right, on the functions that are piecewise linear and continuous, with some mesh size small h. H is the inverse of capital N, the number of nodes, basically. And let us make the problem to become finite dimensional. Then, given that this is a finite dimensional problem, now I can solve it. This is linear algebra. Numerical linear algebra. I can solve this problem by just iterating the gradient descent algorithm. And then, with some little work, a bit of finite element interpolation theory, not only you can prove that this problem now in the finite dimensional setting has a unique solution, but you can even give estimates on the proximity of the actual solution in terms of the solution of the finite element problem UH. So this was a revolution. This was a huge revolution. So 50 years before, people were struggling to understand PDEs, using green functions that were impossible to be computed. 50 years later, with this modern perspective to partial differential equation, very much based on functional analysis, people had a very good understanding not only of the PDEs, but how, to do numerical approximations. Okay, very good. But now, these days, we have learned about neural networks, right? So we know now, according to Wiener and Sivenko, that, of course, you can use classical finite element interpolation to, given a function approximated by finite elements, but we can do something else. We can also use, for instance, the theorem of Sivenko and say, listen, when I take k neurons, right? When I take k neurons, I can also consider the manifold of functions that are represented by these k neurons, right? And then replace the problem of minimizing the original functional in the whole Hilbert space or in a finite element basis. I can just do it based on these answers. Because as k goes to infinity, the space of these functions is dense, then the minimizers of this problem in this, k d plus 2 dimensional manifold will converge to the minimizer of Hilbert. So that will be, something like a neural network variational perspective, right, for solving partial differential equations. Now, there is, however, a very significant gap, right? There is, however, a very significant gap, and the gap is due to the fact that while here, given that the mesh is, fixed, this subspace of piecewise linear functions is really a linear subspace of the Hilbert space, right? So the grid is fixed. We are in the context of linear approximation theory. Therefore, we are minimizing the functional in a linear subspace. When we move into this neural network perspective, this ansatz is nonlinear on the parameters A and B. And this, even if the dimension is finite, is not anymore a linear subspace. This is a nonlinear manifold. This is a nonlinear manifold. Okay? And therefore, even if the functional is quadratic and convex, the problem of minimizing this quadratic convex functional in this nonlinear manifold becomes non-convex. Right? So then, in this setting, the paradox is, well, I can claim that I have a gamma convergence result. I can claim that if I compute the global minimizers of these functionals over these manifolds Mk, and I let k go to infinity, by doing this, I can claim this gamma convergence result, assuming that the minimizers of these functionals will converge to the minimizer of Hilbert and Sobolev. But the problem is how I'm going to get the minimizers of this problem if the problem is non-convex. That's the difficulty, okay? So you see that, you know, when you try to employ neural networks for partial differential equations, there is a big loss. And the loss is that due to the nonlinear nature of the ansatz of neural networks, you lose, you know, the convexity of the minimization problem. Okay? So now, there is something we can do. So in analysis, whenever a problem is non-convex, there is something you can do. If the problem is not convex, you can convexify it and make it convex, right? So what is convexification? You certainly know, right? So you take, for instance, this functional with two wells. This functional is non-convex, right? So now, if the functional be non-convex, I can take the convex envelope, and then I will build something like this, right? So this will be the convex envelope. What is the convex envelope? The convex envelope is the supremum of all convex functions that are below the graph of the non-convex function, right? So now, of course, this is not the original function. This is just the convex envelope, right? So this will be now a segment here, and then, but now the new function is convex. Of course, now the new functional being convex, I could apply a gradient descent algorithm, right? But you see, depending on how I regulate the gradient descent algorithm, I might get all these kind of minimizers of the convex function, which, of course, this minimizer and this minimizer of the convexification are global minima of the original function, but all these here are not minimizers of the original functions, but actually are points which are lying in between, right? So when you convexify, of course, you make the minimization program, the minimization problem easy, But of course, this does not guarantee that every time you get a minimizer of the convexification, you will have a minimum of the original function. Okay? So now, how does convexification go in this setting of neural networks? It is like, so how do we do this convexification in the context of neural networks? Well, this is the formula that is written there. It's very elementary, but we have to think a little bit on it, right? So recall, this is, for instance, Sibenko's ansatz. Where sigma is, you know, the sigmoid or maybe the ReLU, right? See, sigma is one of these activation functions. So when we adopt this perspective, what we are doing is very simple. There is one space variable, x. And then we choose coefficients W, A, and B in each neuron. There are k neurons. So this is the shallow neural network regime, right? Everything is very easy. So we get, you know, out of this combination, we get a new function. This is a neural network depending on x. So the perspective is very clear. Though, as we said, the dependency on A and B is nonlinear, and this forces us to lose the convexity on the Hilbert perspective to partial differential equations, which is very bad. Okay? Now, the way to convexify this function is to think on each atom a bit differently. So now, let's look to each of these neurons or atoms in this neural network ansatz. What is sigma A dot x plus B? There are two ways of seeing this. You can see it as a function of x with parameters A and B. That's legitimate. Or you can also see it as a function of A, B, and x. This is legitimate as well, right? I can now define a function of A, B, and x, which is defined now in RD cross R cross RD, so that whenever you give me A, B, and x, I cook A scalar x, the scalar product, plus B, and then I apply sigma. So now this becomes a function of three variables. Okay, very good. And now, what happens when you integrate this function, right? So this is the function sigma A, B, x. What happens when you integrate it against a measure depending on only the variables A and B? Well, whenever you have a function of three variables and you integrate this function with respect to two variables, you are left with one function depending on the remaining variable, x, right? Very good. And what is the link between this expression here, in which this function of three variables is integrated against a measure, the one here? What is the link between this expression and this one here? So here I am integrating in RD plus 1. Why? Because I am integrating with respect to A, which is in RD, and I am integrating with respect to B, which is in R. So what is the link of this with this? Well, think, for instance, on the case where the measure mu, right? If the measure mu is just Wj, and then the measure is a Dirac delta sitting on a specific value of A and B given by the coefficients Aj and Bj. When you integrate against a singular measure, which is a Dirac delta, what you get is the evaluation on that point. So if you choose mu to be Wj times the Dirac delta at the point Aj, Bj, what you get here is precisely each of these neurons. So what you see is that from this perspective, the neural network approximation is just a particular case of this representation when the measure mu is the sum from 1 to k of Wj delta Aj Bj. Right? If you take this atomic measure, right, this relaxed representation goes back to the original neural network approximation. And now, what is the advantage of this? Of course, here, right, in this representation, this is a very nice envelope. So you see, in this representation, for instance, you could take k arbitrarily large. Depending on how many atomic masses you take, you will have as many neurons here. So in this relaxed or mean field relaxation of the neural network ansatz, not only you have sums with as many atoms as you wish, you can even take an infinite number of atoms, and you can make this series of atoms to be denser and denser and denser so that it becomes a continuum of neurons. This is what this is representing. So this is representing, you know, not only the accumulation of a countable number of neurons, but neurons that are more and more packed so that eventually they constitute a continuum. Now, okay, so this is, of course, then an infinite dimensional space. The dimension of this space being the same as the space of measures on the parameters A and B in RD plus 1. Okay? So once you have adopted this representation, though, you have a great advantage, is that V, right, V is now represented linearly as a function of the measure mu. And therefore, now if I adopt the perspective of Hilbert, right, I am led to minimize, again, a convex continuous function in a functional space. It's the space of measures. However, as you see, by doing this, I have lost something. I lost something important with respect to the original formulation of Hilbert, right? Because, you know, the point of Hilbert was precisely to preserve here, you know, the scalar product intrinsic to variational formulations to define the Hilbert space, right? In which, in particular, you have the very property that bounded sequences are weakly convergent and, you know, plenty of geometry on Hilbert spaces. While in here, when you adopt this perspective, then you are led to work in the space of measures. But the space of measures is not a Hilbert space anymore, right? So then, when you adopt this relaxation by neural networks perspective to solve the original Laplace equation, you lose a lot because you go back to the original formulation of Hilbert, but you lose the Hilbert structure of the problem. Now you have to work in the space of measures. Okay, but people are used to work in the space of measures. I mean, people, for instance, doing image, the noising, in inverse problems, there are many fields in which, image processing, there are many contexts in which we are used to work in the space of measures. It's not a Hilbert space, but we are used to this. But still, there is another price you pay. And it's the fact that even if you accept that you are going to work in a space of measures which is non-convex, even if you do that, then you lose the coercivity of this functional. Why? Because the beauty of the Hilbert presentation with the Sobolev space is that the norm on this Sobolev space is precisely the one appearing here in the quadratic term of the functional. So this makes the functional to be automatically coercive. While in here, the fact that the functional is bounded and this integral of the gradient square is bounded leads to very, very weak information about this measure, essentially because this is a convolution formula. So this is why here I have taken this picture of this celebrated Esser escalator, Esser treppe, and this is one of these impossible three-dimensional drawings in which you see people that are going up and up and up and up, but when going up and up and up and up, due to the fact that, this geometry is hyperbolic, right, they go back to the same level. So somehow here, this is what happened to us, right? We try to, because we knew already partial differential equation and traditional numerical analysis, but we discovered these results by Sivenko, we wanted to employ this neural networks perspective for numerical analysis. We realized that then we were led with problems of minimization that were non-convex. We tried to avoid the lack of convexity by convexification, but then by convexification, we got into the space of measures, which is non-Hilbertian, and in which we don't understand the coercivity of this functional. Then the only way of tackling this will be to add some, Tikhonov regularization, as we do in image processing and so on, but this will, bring the problem and the methodology even farther from the original solution. So this is really, there is still plenty to be done to really exploit properly the use of neural networks for PDE approximation. The most natural approaches, right, lead to solutions that are really not very efficient. But intellectually, this is a very interesting exercise to figure out, and to really investigate to the utmost, to realize that there is really there a bottleneck that you encounter. There are many things that can be done very easily with neural networks, but when you try to really complete the theory and to make it comparable to the state of the art in a traditional applied mathematics, you see that there is a major obstruction, or two major obstructions. One of them being losing the Hilbert structure, and the other one losing the coercivity of functionals that are trivially coercive in the classical Sobolev context. Okay? Okay, let's have a short break, and then we continue at 10:10. Thank you. do you have questions about this? I think this is a rather important matter, right? Because nowadays there is a lot of literature in computational applied math using neural networks, right? Of course, computationally, this is very tempting, right? Because you can just say this. I mean, and there are other versions of this kind of methodologies, right? Some of them minimize instead of writing the variational formulation of the PDEs, like here, some of them just minimize the residual. This is what is called the PINS, physically inspired neural networks. And then you can just adopt some ansatz like this. Can be also more complicated. You can take multi-layer perceptrons. You can take all kind of neural network architecture. So here I just took this one, the simplest one, just to give you an idea of what the methodology could be. Then this becomes immediately a finite dimensional optimization problem. Being a finite dimensional optimization problem, even if it is not convex, then you can apply some stochastic gradient descent, as Professor Zhao was explaining yesterday in particular, although his focus was more on sampling, but you can employ similar methods for finding minimizers, and then you will get something that you can plot and will certainly look close to the PDE solution. But the question is, can you achieve the same level of guarantees as you do in classical numerical analysis? And the answer is no, you cannot. Because in classical numerical analysis, we depart from this, linear problem with a coercive functional. We make a, finite dimensional projection, and everything here can be tracked. Even the constant here, C, in the finite element theory, can be estimated. Because, this has to do with the shape of the triangles that you adopt in order to, cover the domain omega. So even the constant here can be estimated. And this is now a finite dimensional convex quadratic minimization problem. You can apply a steepest descent algorithm. You can apply conjugate gradient. And again, you know exactly what is the convergence rate of the methodology. So everything can be made quantitative. So you can completely estimate the complexity of the algorithm. You give me an epsilon error, take epsilon, then you can check what is the age you need and how many steps on the gradient iteration you have to do in order to make sure you have this epsilon error. So these methods are, the traditional methods of numerical analysis are high fidelity, right? And this is why, if you go to the ophthalmologist because you have to do eye surgery, you want high fidelity, right? You don't want an error big like this, right? I mean, you wanted eye surgery here, not here, right? I mean, it's the right eye, it's not the left eye, it's the right eye. So you need high fidelity. When you take an airplane, you want guarantees that the airplane will get to destination. Will you fly on a company that guarantees, say, 92% success? I mean, 92% is a lot, right? I mean, it's very good. Yet it means that out of 100 airplanes, 8 crash. Then, okay, so maybe you go by train, right? Then you better take the train. High fidelity is not 92%, right? So classical numerical and applied mathematics offer high fidelity solutions. And everything is well paved. Convergence, we know what it is according to Lack's theorem, is a stability plus consistency. We know about convergence rates. We know how convergence rates are related to the regularity of solutions, right? So this is traditional applied math. Now, when you move into this context, everything is quicker because you can just minimize something based on some neural network concepts. And there are plenty of, Python programs that allow you to do that very quickly. You plot the solution. The solution will very likely look very nice. But if people ask you, what is the fidelity you can guarantee? Then you say, well, with high probability, the solution is relatively close. It's not at the same standpoint, right? So this is why there will be a lot, of work being done in the coming years to really try to merge these two fields, right? The classical numerical analysis and PDE theory with this more modern machine learning and artificial intelligence inspired technique. There is plenty of work to be done, not only at computational level, but especially at a more conceptual functional analysis level, right? Okay, very good. So probably what experts will tell you is that, in processes for which we already have very good numerical solvers, like in the classical industrial processes, right? Like aeronautics, for instance, where, aeronautics has been so successful, right? We know how to design very efficient airplanes, right? So it will not make sense to replace all computational fluid dynamics by these neural network inspired ideas. But certainly, probably, there are aspects of aeronautic industry that are not, easy to model using classical models coming from mechanics, and that can benefit from the use of neural network ideas. For instance, we have seen that large language models is an extraordinary tool, right? And large language models were built massively on the use of neural network and supervised learning, enhanced by this very, original idea of the next token production, right? That was the breakthrough to make, text interpretation, comprehension, become a supervised learning problem. Next token production. The next token is the label, right? So there are tasks where machine learning and neural networks will be extremely useful, but probably the goal is not to replace classical numerical mathematics by these ideas that seem to struggle to provide the same level of, reliable methodologies. Very good. Let me then continue. So, and then there are already, several papers and many people saying, well, be careful. It's good to know about machine learning, but trying to solve PDEs with machine learning solely, this will probably, lead to situations where, you realize, as I said, you cannot guarantee the same level of high fidelity. Very good. Let me move forward. Now, so this is work we have been doing recently. In particular, this has been done by Sikian, right? With this goal of trying to merge traditional applied mathematics with these machine learning inspired ideas, then we thought of the following. Okay, so assume, for instance, you have to model dynamic data, right? So you have to track or model dynamic data. So imagine, for instance, I have here, how many? 1, 2, 3, 4, 5, 7, I think, 7. So we have 7 sensors, right? 7 sensors located somewhere in Changchun City, and they are measuring data about what? It can be either temperature in different locations, it can be density of traffic, it can be the humidity of air, it can be pollution, it's maybe 7 different, assets in the Chinese stock market. It can be the price of housing in 7 different neighborhoods in Changchun. I don't know, it can be the ranking of 7 different high schools in Changchun. It can be anything, right? You just get information about 7 different realizations of the same variable. And then you have it at a given time, t equals 0, black. You have it at t equal 1, blue, right? And time units can be arbitrary, right? If we are talking about ranking of high schools, these are values that you will get only once per year. If this is, temperature being measured by, thermometers, this will be almost real time. So this will be every second, basically, right? If this is the value of the stock market, then you will get an output every day when the stock market closes. So the time periodicity can, vary from one application to the other. But the idea is always the same, At time equals 0, you get some values. Time equal 1, you get others. Time equal 2, you get others, and so on. And now the question is, can you build a dynamical system, right? So these are just pure data. So we are now purely data-driven. Here, there is no mechanics. I don't even know what the application is, right? I don't know whether this is a problem on finances or meteorology or, steel industry, aeronautics, I don't know. So this is purely data-driven. And then I ask you, can I build a neural network dynamical system that is interpolating all this data? And then the answer is yes, we can, right? Of course we can. We can do that. So Sikian did the video. He can tell you, maybe you can explain in Chinese what the video does. Yeah. So it's very pretty, right? So what does, in your opinion, the video do? What does, in your opinion, the video do? What do you think it does? So we have shown before that, for instance, neural differential equations using this zigzag strategy of the Rubik cube, using control theoretical ideas, we have shown that, these neural differential equations were able to bring simultaneously n dots from the initial configuration to the final configuration. So we have learned how to move, right? We have learned how to move from the black configuration to the blue, right? And once we know how to move from the black to the blue, then I know how to move from the blue to the green. And then I know how to move from the green to the yellow, and from the yellow to the red, and so on. So I just iterate. You see that just the iteration of the methodologies we have built to show using neural network models how to move data from some initial configuration to the next one allows us to iterate and build okay? So this is something you can do. And there are many, neural network architectures, able to do this in different ways. There is the so-called reservoir computing methodologies. There are long, short memory networks. There are, different ways of doing this, right? You can do it so that, this becomes adaptive. Whenever you get new data, you continue, keeping track of the data and so on. This is, dynamic data tracking. But there is no physics on it, okay? Very good. Now, but in practice, very often, there is physics. And because there is physics, we have some, ordinary or partial differential equation model, maybe also with some noise and some uncertainty and some errors, but we do have some model for approximating, for modeling the phenomena under consideration. So now, you see, something you can do related also to neural network employment is the following. You say, oh, assume you give me the ordinary differential equation here, right? So that we all understand. If F is Lipschitz in X, uniformly on T, we know the Cauchy problem has a unique solution. The solution evolves regularly on time. You have a stability estimate using Gromval inequalities. So we know everything we need, right? And you say, what is the ODE doing? The ODE is driven by this vector field on the right-hand side, which depends on X and on T. But now, we have the theorem of universal approximation. What does the theorem of universal approximation say? The theorem of universal approximation says, give me a vector field F, depending on X and T, but I don't mind that this is X and T. I mean, I could just consider X and T to be a big X. After all, X is in dimension D, is the D dimension of this dynamical system. T is one variable, so X comma T is just a new Euclidean variable in the space of dimension D plus 1. So I can still apply the existing theorems of universal approximation, and now this is what I get. For instance, this is the paper I was mentioning by Pincus, 99, where he generalizes the paper by Sibenko by showing that, in fact, you get the same result as Sibenko for all activation function, right, sigma, which is not a polynomial. Okay? So take any activation function sigma which is not a polynomial, for instance, the ReLU or the sigmoidal function, and this is what the universal approximation theory tells you. You can basically reproduce up to an arbitrarily small error the vector field F by this expression here. You see, until now I was writing A dot X plus B, and now I write A1 dot X plus A2T. Why do you think I need now this second term here? Well, we need this second term here because now I am applying the theorem of universal approximation on the variables X and T. And the ansatz of Sivenko is that wherever the independent variable X is, you need to multiply scalarly this variable by the coefficient A. So in this case, this product of A times the vector xt leads to this two-component splitting, A1x plus A2t. So now, of course, this leads to the fact that if the vector field here, F, is non-autonomous, then the neural network ansatz you get, the neural network approximation you get, is also non-autonomous. But you see, however, there is a beauty here, is that somehow, the coefficients in this approximation are time independent. So this is a non-autonomous dynamical system. It is true, because as dynamical system, this depends, the nonlinearity depends on time, but through coefficients that you can compute a priori out of the, say, neural network approximation of the vector field, right? And this is what we have called in our paper, this is done with Sikian Alonso, Lorenzo Liberani, and Kang Liu. Lorenzo is a postdoc in our team, and Kang is now a professor in France. He was with us last year. I think he will be coming tomorrow. So this is what we call semi-autonomous ODE, right? Or neural ODE. Why semi-autonomous? Well, because it depends on time, but we say semi-autonomous in the sense that in order to build this neural ordinary differential equation, the only thing you need is coefficients W, A1, A2, and B, which are independent of time, right? So this is a natural class of dynamical systems inspired on neural network approximation theory, on the universal approximation theorem, and that allows to approximate the solutions of any non-autonomous dynamical system. So this is a different way of employing neural network for dynamical system. The first one was, I do it purely data-driven. The second one here is the opposite. I do it if I know the model, I can replace the model by this neural network version, okay? And this is something that Sikian did in his simulations, right? So we used these neural network ideas to, for instance, simulate this Doswell frontogenesis. So Doswell frontogenesis, this is a paper that is not so well known in the community of applied mathematics. It's a paper written back in '84 in meteorological sciences, which, here you see exact. He builds an explicit transport equation. So you see, let's read this transport equation. This is time derivative of rho, the density, plus the divergence of rho times a vector field. So this vector field that can be written in an explicit form over here, right, generates a tornado, a vortex, right, for, describing this kind of tornado phenomena in meteorology, in which you have essentially an initial datum, which is a smooth transition between, say, -1 and 1, like in here. So you have cool air and hot air separated by a flat interface. But because you are solving this hyperbolic transport equation in which the velocity field is rotating, then the particles, both of cold and red hot air near the interface, start rotating, and they develop this kind of very complex tornado vortex architecture. Now, of course, this transport equation is related to the differential equation I was discussing here, right? Why? Because, well, this transport equation, as we know, the solutions are simply given by are computed transporting the mass of the initial data, in this case, this hyperbolic tangent that is, approximating smoothly this Bang function mixing hot and cold air up and down, right? So this solution of the transport equation is just computed by transporting the initial condition along the characteristics of the differential equation corresponding to this vector field over here, right? This tornado vector field. So we can apply these ideas, right? And this is what, Sikian did in this very nice simulation. Now, in this simulation, what Sikian tackles is the following. He says, okay, now assume, right? I don't know the full PDE, because as I said, if you know the full PDE, the first thing you can do, and this is what is plotted here, if you know the PDE, then you know the vector field, then you know the nonlinearity in the ODE of the characteristics, you can do neural network approximation and replace this neural network this ODE by the neural network version, and then you will have a neural network version of this transport equation that will lead, to the simulations in the top that are extremely good on capturing the original dynamics of the transport equation. But when doing this, we have used the fact that we know explicitly the vector field generating the dynamics. So the next question was, let's move further. So in practice, when you are in a meteorological context, maybe you know the initial configuration. You are considering this situation where you have hot air separated by an interface and cool air. Of course, interfaces in nature are not necessarily flat. So here we are considering flat interfaces in order to better understand how the complexity of the interfaces grows as time evolves, right? And then what Sikian said was, okay, instead of assuming that I know the vector field, now I don't know the vector field. But I have a number of, thermometers, right, placed along the city that are giving me, measurements on these locations along time. And the question is, can I reconstruct, the global evolution of the density in this fluid mixing problem out of the information that is recorded in these thermometers, in these sensory locations? And the answer is yes, you can do it pretty well. Why? Because again, you can interpolate the data measured on these sensors through a neural network ansatz, and this neural network ansatz allows us, to build a transport equation that will be solved numerically efficiently, leading to this, nice numerical simulation. Okay, so then, of course, there is no miracle here, right? You can say, oh, it's very nice. Then you look closer and you say, well, it's very nice, but high fidelity is not guaranteed, right? Because you see, when you look, you know, the pattern is fine. The global pattern of the tornado is fine. But we have the impression that we are losing fidelity, precision here, right? Of course we lose precision. Why? Because we only have information coming from a discrete set of sensors. And there is no magic, right? If you give me more sensors, this simulation will be sharper. If instead of taking all these sensors, how many sensors are here? Like 64, or how many are there? 400 sensors. So with 400 sensors, you get this. Of course, if instead of 400 sensors, you take 40 sensors, you will get much less resolution. And if instead of 400 sensors, you take 4,000 sensors, you will get much better resolution, right? So then, you know, the message of this part of the talk is to say, if we have to merge PDE-based knowledge and data-driven knowledge by means of machine learning tools, we can do that, but this has to be done carefully. It's not just solving PDEs using machine learning, but is more elaborate than this, is to make a smart use of machine learning to deal with the data information you are provided, and always keep in mind that there is no miracle, right? So the level of precision you can aim is very much conditioned by the data you are given. And this is why sampling, as we said yesterday, is so important, right? So please don't expect that, you know, machine learning will solve problems if you don't feed the machine sufficient information about the process you are aiming to, you know, to deal with, okay? So sampling, building the data set is essential, and you will never get more information as the one that is contained on the data set you have provided to the machine. This is something we see clearly here. So again, I repeat, can we merge traditional applied math and machine learning properly? Yes, we can, but you know, for this, you have to do things properly and don't expect magic. I mean, the output of the results you will get will be commensurate to the quality of the data you have, okay? So, and this is something we are doing now. This is joint work again in collaboration with Lorenzo Liberani, postdoc in our team, and Thijs, a PhD student, Thijs Steinberg in our team as well in Erlangen. So we are trying to write this in a more systematic manner. I just show you the scheme of what we do. The idea is the following, right? As I said, I don't think the key of applied math is to say, oh, we abandon all, you know, functional analysis and PDEs and all the classical numerical analysis, and we will do it using machine learning. No, no, this is not the idea. So we have to keep all we know. So all the know-how we have achieved, right, on, you know, physical models using mechanics and solving PDEs using functional analysis and numerical analysis, we keep all this, right? Now, the question is that now, very often in practical applications, right, we have observations as well, right? So these observations allow to enrich the physical model that we know from, say, physics and mechanics with one which is purely synthetic. Like the yes we can model we have built, ignoring completely the physics just by interpolating data using neural networks, right? And then you can try to make these two models cooperate. How do you make them cooperate? Well, you have the model from physics, you have the synthetic model coming from data, and now you try to push them, right? So that they get closer and closer and closer mutually. So this is like a Nash equilibrium, right? I don't expect the two models to coincide. Why? Because probably there is not PDE in the class I have chosen that is able to interpolate the data exactly. And there is no synthetic model I can aim that can reproduce, right, the PDE I have chosen exactly. Probably they will never coincide completely, but I can aim to make the gap to be smaller and smaller and smaller. And for this, the natural way to proceed in game theory is to minimize, with respect to one variable and the other, the distance in an alternating manner. This is something that, of course, we know converges for potential games. In general, doesn't necessarily need to converge, but it's probably the best we can do in order to try to get, close to this Nash equilibrium. So once we stop the process, what do we expect? We expect to have two models, not one, two. One will be the PDE model, fulfilling the PDE, but with the parameters identified so that they track the data provided by the observations in the best possible manner. And on the other hand, we will have also a synthetic model, which is tracking the data, but because it has been challenged to get closer and closer to the PDE, it's a quasi-solution, it's an approximate solution of the PDE to some extent, right? So I think this is the future, one of the future possible developments of applied maths employing machine learning ideas is to hybridize synthetic data modeling using tracking using neural networks and PDE approximation using classical functional and numerical analysis. And this is a classical, I think this is a parameter identification problem for Helmholtz equation, right? So there were like two, say, coefficients to be identified, right, on the Helmholtz equation under consideration. The red dots, I think, is the sensor location information we provide. So you see you have electromagnetic waves in this square, but we only have information on this upper, say, top right quadrant, right? So we have only information on, say, 25% of the domain, yet we can guarantee some level of approximation with respect to the true coefficient. So actually, you see the true coefficients here is one Gaussian for the coefficient k and another Gaussian for the coefficient eta, which are localized basically in this southwest corner, right? So this will be what? Chengdu, right? This is what, Chengdu? And this northeast corner is Changchun, right? Yeah, okay, so you see, you have one Gaussian is in Chengdu and the other Gaussian is in Changchun. This is the true solution. Now, when you do it just by using classical parameter identification techniques, right, for using only the PDE, right, without using this sensoring information, is very, very hard, right? And you get very low precision on the location, in particular of the Chengdu. You don't see the Chengdu, Gaussian. When you do it just using pins, you see one, but you miss the other. And of course, when you hybridize, then of course you see both of them because you are enjoying, right, of the advantages of both employing the physics and employing the machine learning ideas, right? And this is something you see also when you look to how the cost, functions saturate in each of the different methodologies we employ. By doing this hybrid strategy of combining both the mechanics, PDEs, and the data-driven, we can outperform all other approaches. So there is plenty to be done in this field. You are all invited to try to contribute to this area. I will let the slides of my talk here with you. You will find some other references in our team. And as I said, I invite you all to try to contribute. I mean, without quitting your field, right? I mean, if you are a probabilist, keep doing probability. If you are a PD analyst, keep doing PD analysis. If you are a numerical analyst, continue doing numerical analysis. So you don't need to quit your field, but you can certainly think from your field on, some of the challenges in this, very rapidly evolving broad area. And there are questions of, like two different natures. And these are the two topics I have tried to present here, right? So some questions are more fundamental, right? It's more about the mathematical aspects of machine learning. So why does it work? Why, does it work that well? Why also sometimes we have difficulties to go beyond this 92% that, is an impediment, a wall, an obstruction to get to high fidelity, right? How can we develop better methodologies for doing this? And then the other one is more the more applied math perspective, right? Is to, to play smart and for specific applications that you might have in mind, try to develop these digital twins like methodologies that combine both classical applied math together with, these new artificial intelligence methodologies. There is plenty of work to be done, in particular when you are dealing with relevant applications such as personalized medicine, right? So, I mean, you don't need to convince anyone that this is important. Everyone knows that this is important. Health is important, right? So you don't need to discuss this in depth. Environment, climate, right? Energy, natural resources, all this is critical for every society, and therefore, any contribution in this field that is oriented into these directions certainly will have the support of, the science foundations in all countries. So this is a very promising area, I think, to join as well. Okay, thank you for your attention. It was a great pleasure being with you.